At a concert one night, a woman closes her eyes as the first chord plays. She doesn't just hear the music, she watches it. The opening note arrives as a wash of gold, and as the melody deepens, the gold slides into a heavy shade of blue. She has never known it any other way. To her, this is not imagination. It is simply what sound looks like. Most of us grew up learning there are five senses: sight, hearing, smell, taste, and touch. It's a tidy list, easy to memorize, and almost completely incomplete. Scientists studying perception count far more channels than that, including your sense of balance, your sense of where your limbs are in space, and your sense of what's happening inside your own organs. That sense of limb position is called proprioception, and it's the reason you can touch your own nose with your eyes closed without ever looking at your hand to check where it is. The sense of your internal organs is called interoception, and it's why you can feel your heart pounding after a scare or notice hunger building before your stomach makes a sound. Both of these run constantly in the background, mostly unnoticed until something goes wrong with them. People who lose proprioception due to rare nerve damage have to consciously watch their own limbs just to walk, because their body no longer tells them where those limbs are on its own. So the five senses were never the full picture. They were a simplified model built centuries ago, long before neuroscience had the tools to look inside a working brain. And within the fuller picture, human experience does not always follow the rules. Some people taste words. Some people feel a stranger's touch on their own skin just by watching it happen. Some people, without ever seeing a wall, can tell it's there. And a small number of people can be seriously injured and never feel a thing. These are not comic book abilities. They are documented, studied, and in some cases, life-threatening. This is a tour through the rarest ends of human sensation, moving from the relatively common to the almost unbelievable, and asking one question the whole way through. What is a sense, really? And how far can it bend before it breaks? Let's start with the woman at the concert. What she experiences is called synesthesia, a condition where stimulating one sense automatically triggers another. The most studied form is called grapheme color synesthesia, where letters or numbers each carry a fixed, involuntary color. For someone with this trait, the number 7 might always look red, no matter the font, the ink, or the context. Another form, chromesthesia, is what the woman at the concert has: sound that produces color. Researchers estimate that synesthesia in some form appears in roughly 4% of people, which makes it far more common than most people assume, since many synesthetists simply think everyone experiences the world this way, until they mention it out loud and get confused looks in return. Brain imaging studies suggest the cause lies in how the cortex is wired during early development. In a typical brain, regions responsible for processing color and regions responsible for processing sound or language develop with clear boundaries. In a synesthete's brain, those boundaries appear to be less sharply drawn, allowing activity in one region to spill into a neighboring one. This is sometimes called cross-activation, and it isn't a malfunction so much as a different wiring outcome, one that shows up more often in people with a family history of the trait, and interestingly, more often among artists, musicians, and writers. Composer and painter Wassily Kandinsky reportedly described hearing color as he painted, and while such historical accounts can't be verified with modern brain scans, contemporary synesthetes have been tested extensively, confirming the trait is real, consistent over a person's lifetime, and involuntary. That last point matters. Synesthetes don't choose to see colors and sound. They can't turn it off. And once you understand that the brain can automatically connect two senses that most people experience separately, a stranger question follows. What if the brain connected your senses to someone else's body? That is precisely what happens in a rarer and more emotionally complex form of the condition called mirror touch synesthesia. People with this trait feel a physical sensation on their own body when they simply watch another person being touched. Watch someone get tapped on the shoulder, and a mirror touch synesthete may feel a tap on their own shoulder in the same spot. Watch someone wince from pain, and they may feel an echo of that pain themselves. This isn't empathy in the emotional sense. It's a literal, physical, involuntary sensory response, and researchers estimate it may affect somewhere around 1 to 2% of people, making it noticeably rarer than standard synesthesia. The suspected mechanism involves what neuroscientists call the mirror neuron system, a network of brain cells that activate both when we perform an action and when we watch someone else perform it. In most people, that mirroring stays mostly internal, quietly helping us understand and predict other people's actions and intentions. In mirror touch synesthetes, researchers believe that internal mirroring crosses over into actual sensory experience, blurring the usual boundary between self and other. Some studies have found that people with this trait score higher on measures of empathy, which raises an intriguing possibility. For some people with mirror touch synesthesia, this can make everyday environments genuinely exhausting, since a crowded train or a busy street means a constant, uninvited stream of physical sensations triggered by strangers they'll never speak to. Researchers studying the condition have used simple mirrored touch experiments to confirm it's measurable, tracking where on their own body a participant reports feeling a sensation while watching a video of someone else being touched, and finding the reported location consistently matches the location shown on screen. Rather than being simply a strange quirk, mirror touch synesthesia may sit at the extreme end of a spectrum that all human brains share, the same underlying system that lets any of us tense up watching a stranger stub their toe. So far, every trait we've covered involves senses blending together. But some of the rarest sensory stories involve a sense being rebuilt entirely, from parts the brain wasn't originally meant to use that way. Consider echolocation, the ability some blind individuals develop to navigate using sound. By making sharp clicking noises with their tongue and listening to how those clicks bounce back, some blind people can detect the size, distance, and even the general shape of objects around them, including walls, furniture, and parked cars. This isn't the sonar of a bat evolving inside a human body. It's a learned skill refined over years of practice, and it draws on remarkable brain plasticity to work. Brain imaging studies on trained blind echolocators have found something striking. When they interpret click echoes, activity appears in the visual cortex, the brain region normally responsible for processing sight. In other words, a part of the brain built for vision doesn't go dark just because the eyes stopped sending it signals. Instead, it appears to get repurposed, taking in a completely different kind of information and using it to construct something functionally similar to spatial vision. This finding reshaped how scientists think about blindness itself. For a long time, the visual cortex was assumed to sit idle without visual input, essentially a piece of unused hardware once the eyes stopped supplying it with signals. Researchers first began seriously studying human echolocation in the early 2000s, using controlled experiments where blind participants navigated mock obstacle courses using nothing but tongue clicks and their own hearing. The results were consistent enough to rule out guesswork or coincidence, with trained participants correctly identifying object position, size, and even material differences between surfaces at a rate far beyond chance. Later brain scanning studies confirmed what the behavioral experiment suggested, that this wasn't just clever listening, it was genuine repurposing of visual brain tissue for an entirely different sensory job. Echolocation research suggests otherwise. Unused neural real estate doesn't stay unused for long. It gets recruited by whatever sense demands the most attention. This is only possible because of neuroplasticity, the brain's capacity to reorganize itself based on experience, and it explains why practiced echolocators tend to outperform beginners regardless of how long they've been blind, since the skill depends more on training than on any innate trait. It's a powerful reminder that a sense isn't really about the eyes, the ears, or the tongue. It's about the brain's ability to extract useful patterns from whatever raw signals it receives, wherever those signals come from. Now let's turn to senses that aren't rebuilt or rewired, but simply turned up. Roughly a quarter of people are classified as supertasters, meaning they have a significantly higher density of taste buds than average, making bitter, sweet, and spicy flavors feel far more intense. This trait is closely tied to a person's genetic response to compounds called PROP and PTC, chemicals used in labs to test bitterness sensitivity, and supertasters often report that foods like broccoli, coffee, or dark chocolate taste overwhelmingly bitter compared to how other people describe them. While being a supertaster is common enough that it isn't especially rare on its own, the far end of that spectrum, sometimes called hyperosmia when it comes to smell, is much less common and involves an extraordinarily heightened sense of scent, to the point where ordinary environments, perfumes, or even everyday household products can feel physically overwhelming. People with hyperosmia sometimes struggle in public spaces filled with competing smells, since their brain can't easily filter out the sensory noise the way a typical nervous system does. Researchers are still working out exactly why some people's smell and taste receptors are so much more sensitive. But the leading theories point again to genetics, this time affecting how many receptor cells a person has and how efficiently their brain processes the signals those cells send. It's a useful bridge to our next case because it shows that heightened sensation isn't automatically a gift. Depending on the environment, it can just as easily become a burden. There's one more heightened sense worth pausing on because, unlike the others, it isn't about the nose or the tongue at all. It's about color, and it lives almost exclusively in women. Most people see the world through three types of cone cells in the retina, each tuned to a different range of light, roughly corresponding to red, green, and blue. The brain combines signals from those three cone types to build the range of colors we call normal human vision, somewhere around 1 million distinguishable shades. Tetrachromacy is a rare condition in which a person has a fourth functional cone type, sensitive to wavelengths that fall between red and green, and it can theoretically allow the brain to distinguish colors most people cannot separate at all, pushing the visible range toward the tens of millions. The reason it shows up almost exclusively in women comes down to genetics. The gene responsible sits on the X chromosome, and because women carry two X chromosomes, some inherit one standard version of the gene and one mutated version, creating the possibility of a fourth cone type working alongside the usual three. Men with only one X chromosome generally don't get that same genetic opportunity. Researchers estimate that while a meaningful percentage of women carry the genetic mutation involved, only a small fraction go on to develop cones that are functionally active enough to produce true tetrachromatic vision, making confirmed, tested cases genuinely rare. Testing for it isn't as simple as an eye exam. Researchers use carefully controlled color-matching tasks, presenting subtle shade variations that a trichromatic brain literally cannot tell apart, to see whether a subject can consistently separate them. Most people who carry the genetic potential never get formally tested at all, which means the true number of functional tetrachromats in the world remains an estimate, not a confirmed count. And that brings us to the rarest and most dangerous sense on this list. Not too much sensation, but none at all. Congenital insensitivity to pain, often abbreviated CIP, is an extremely rare genetic condition in which a person is essentially unable to feel physical pain from birth. It typically stems from mutations in a gene called SCN9A, which plays a critical role in how pain signals travel along nerve cells to the brain. In people with CIP, that pathway is disrupted, meaning an injury that would make most people cry out in agony. A burn, a broken bone, a deep cut, produces no warning signal at all. This might sound appealing on the surface, but doctors who study the condition describe it as one of the most dangerous sensory disorders known, precisely because pain exists for a reason. Pain is the body's alarm system, telling us to stop touching something hot, to rest an injured limb, to notice when something inside us is going wrong. Without that alarm, children with CIP have been known to bite through their own tongue while teething, walk on broken bones without realizing it, or fail to notice serious internal injuries until they become life-threatening. The condition was first clearly linked to the SCN9A gene by geneticists studying extended families in Pakistan in the mid-2000s, where several relatives shared the same striking trait. None of them had ever experienced physical pain, and each of them carried the same genetic mutation, giving researchers their clearest look yet at exactly which gene was responsible. Because the condition is so rare, with only a small number of confirmed cases documented worldwide, most doctors will never encounter a patient with it in their entire career, which makes early diagnosis difficult and dramatically raises the stakes for families managing the condition, who often have to visually inspect a child's body daily just to catch injuries their child cannot feel. Some children with CIP are misdiagnosed for years, since a toddler who shows no reaction to a painful injury can initially look to an untrained observer like a child who is simply unusually tough, rather than one who is receiving no pain signal whatsoever. Researchers studying CIP aren't just documenting a rare disorder, they're using it as a map. Because the SCN9A gene plays such a precise role in pain signaling, scientists studying CIP patients have been able to identify potential new targets for pain medication, hoping to develop treatments that could someday dial pain down for chronic pain patients without eliminating the nervous system's other functions the way current painkillers often do. So, what connects a woman who sees music, a person who feels a stranger's touch, a blind man who navigates by sound, a woman who sees tens of millions of colors most eyes can't separate, and a child who cannot feel a broken bone? On the surface, these traits look like completely unrelated curiosities. Underneath, they share a common thread. Every one of them comes down to how the brain wires, prunes, and interprets signals, not to some fixed universal blueprint for perception. During early brain development, the nervous system forms an enormous number of neural connections, far more than it will ultimately keep. Over childhood, a process called synaptic pruning trims away the connections the brain doesn't use, sharpening its wiring based on experience. The same way a gardener cuts back overgrown branches so the healthiest ones can get more light. A newborn's brain, in fact, shows far more cross-wiring between sensory regions than an adult's does, which is one reason some researchers suspect every infant may briefly experience a mild, unrefined version of synesthesia before pruning sharpens those boundaries. In most people, this process cleanly separates sensory regions from one another. In synesthetes, some of those boundaries stay more permeable. In trained echolocators, unused visual pathways get claimed by an entirely different kind of input. And in conditions like CIP, a single genetic change can interrupt one specific signaling pathway while leaving every other sense completely intact. None of this means the brain is randomly glitching. It means the brain is doing exactly what it always does, building perception out of whatever signals and structures it has access to, and doing it slightly differently in every single person. The five senses we learn as children were never a hard limit. They were always closer to a rough sketch of something far more flexible and far stranger underneath. Back at that concert, the music fades and the woman opens her eyes. For her, the fading gold and blue disappear along with the final note. Just another ordinary night of hearing a song the way she always has. Somewhere else, a person walks confidently through a crowded room, reading the space around them through quiet clicks most people would never think to make. And somewhere else, a parent checks their sleeping child's arms and legs. For bruises the child never felt happen. Three completely different lives, three completely different relationships with the world, all built from the same basic material. A brain interpreting signals, one connection at a time. None of them are broken versions of a standard model. They're proof that there was never really a standard model to begin with, just billions of brains, each wiring itself slightly differently in response to the life it happens to live. The next time someone tells you they experience the world differently than you do, they might be telling you something more literal than you realize.